Hello everyone, ciao amici di Creators Talks. Tonight we have a great biohacker, and is David, is here. E oggi parleremo un po' italiano, un po' inglese, quindi perdonatemi il switch di
Sì,
lingua.
ragazzi, abbiate pazienza, sarà una puntata estremamente interessante e quindi abbiate pazienza per questo cambio di lingua. Allora,
Very welcome to our guest, David Ishee. Ciao,
Thank you,
David.
David, to be here.
No problem. Thank you guys for having me.
And you want to start from?
Yeah, I would like to introduce you, David, for our Italian community. Quindi, ragazzi, David è un biohacker, come avete sicuramente visto nel documentario di Netflix. Lui vive in Mississippi, if I'm right.
Yeah.
And si occupa, il suo lavoro principale è allevare cani, ha dei cani meravigliosi. How many dogs do you have at the moment?
11.
11, nice. Quindi oggi andremo insieme a David a scoprire il mondo del biohacking, ok? Quindi gli faremo domande in inglese, poi con il supporto di Gian andremo a tradurre e a spiegarvi quello che ci sta dicendo. Sì, si trova nel suo laboratorio in questo momento.
Are we in your lab, David, right?
We are.
That's
Yeah.
great.
Yeah, this is mostly just like storage behind me.
Okay.
Like there's a whole bunch of like my equipment piled up right now because I've got a whole bunch of crazy stuff going on. But like, yeah, I mean, I'm within arm's reach of all my stuff right now.
Okay, let's start easy, David. What is biohacking?
Biohacking, the way I think of it is it's doing genetic engineering, life sciences kind of stuff, but outside of an institution. So you're not part of a university or a company. You're just sort of a DIY biotechnology.
Okay,
In
so
my case, go ahead.
vai Fra.
Yeah, so basically it's doing genetic engineer outside the mainstream scientific community, right?
Right.
I
So
didn't know these particular details about the outside world, so the the non-academic world. So the point is, for our Italian friend, David dice biohacking è occuparsi di ingegneria genetica fuori dal mondo accademico, outside the academic world. Ok.
and also outside sort of corporate labs and stuff like that.
E fuori dal mondo delle corporation.
Yeah. So some people refer to it as like citizen science and that sort of stuff.
Yeah, because basically the thing is mainly in United States, but I think it's the same thing all around the world. There is this pharmaceutical how do you say, like the big corporations in the pharma corporations, and they pretty much control everything, because you guys in US have a huge lobbyism. So if there is not like economic interest, like some stuff is not gonna came out.
Right. And even there is some government incentives for like orphan drugs and things like that. So like if you have a condition that's very expensive to treat, but only a very small number of people actually have it, there are some government incentives to sort of motivate companies to try and develop cures for those things. But you know, those incentives only go so far. So if it's something that only affects 2 or 3 people, nobody's going to work on it.
Yeah, exactly.
But that's the thing. If you're one of those people, you could work on it.
That's interesting.
That sounds great.
That's interesting. Praticamente ci sta dicendo che con c'è tutta una lobby farmaceutica che si occupa di queste cose qui a livello istituzionale, ma si occupa solamente dei casi che riguardano tante persone. Quindi se tu sei uno di quei pochi casi che quindi non si mettono a studiare la cura per i tuoi problemi, però this is where biohacking arrive, cioè qui è dove il biohacking si inserisce, potendo trovare tu stesso le cure, diciamo, per i tuoi problemi.
So before diving in the biohacking world, I would like a brief introduction about who you are. Who's David Ishee?
So I got into all this because I'm a dog breeder. I love dogs. I've always loved dogs. My family's bred dogs forever. And in particular, I breed a type of working mastiff. So they're big dogs. They're bred for protection work. And mastiffs in general are very unhealthy. So I've been trying for the last 10 years to make a healthier, more athletic, more capable working mastiff. And then I started a project to extend what's possible because selective breeding only gives you so much. But now with new technology like CRISPR and genetic engineering, if you can apply those things, because we've made a lot of genetically engineered animals, lots and lots of them, mostly mice. But if you can use those tools for dogs, you could cure all the genetic diseases. And a lot of people don't realize that dogs have more genetic diseases than any other species.
Yeah, because from what I know, dog breeding is like made a lot of, let's say, mistake in the time. Like if you take those dogs would have like breathing problems because they just keep mixing them, and without like a real knowledge about it. It was just something you could do, like make two dogs having fun together, and then you had no idea what the DNA came out.
Exactly. And then also things like selecting for traits that just don't work, like a really smashed face, like people like bulldogs with really, really short noses. But dogs have all kinds of structure inside their noses. So if you cram it all into a very small space, it's hard to get air through there. And it's hard to cool, because a lot of people don't realize that dogs' brains are air cooled. So like all that surface area is part of what cools their head. So when you have a really smashed face, they overheat, they have all kinds of problems.
So it can actually also affect their behavior.
Yeah. Oh yeah. Yeah. And there's also a bunch of neurological problems that are associated even just with morphology. There's some dogs that are bred in such a way that their brains eventually outgrow their skulls. And that puts pressure on the brain and causes brain damage. Yeah.
Wow. I didn't know about that. That's
So
very, very interesting.
Breeders have made a lot of mistakes, and a lot of it's also come down to the breeding methodology, like extremely small breed or gene pools, a lot of inbreeding, those sorts of things, sort of manifest these problems over time. And I don't think that like the path to breed all these problems out is hundreds of years long, but to genetically engineer them out, we could do in a generation. We just have to do it.
Yeah, that's wonderful. Gian, we're gonna like translate this beautiful exchange we just had.
Yeah. Vai tu.
Allora, ragazzi, fondamentalmente ci stava raccontando del fatto che, visto che lui si occupa da generazioni di allevare proprio, creare cani di razza e con certe caratteristiche, uno dei problemi dei cani, appunto, visto che la maggior parte delle specie che abbiamo sono una conseguenza di mix che abbiamo fatto noi umani, proprio allevandoli, è che magari ci sono delle caratteristiche morfologiche, vedi ad esempio i bulldog, che hanno dei problemi proprio di morfologia, quindi quelli con il naso molto schiacciato hanno problemi per respirare, hanno problemi per ossigenare il cervello, piuttosto che in alcuni casi estremi si arriva proprio al fatto che il cranio del cane è troppo piccolo per ospitare la crescita del cervello, quindi è proprio dei danni cerebrali causati proprio da queste meccaniche fisiche.
So David, did you start all this biohacking to go into this biohacking world to implement, to empower your job with dogs, right?
Yes, that was the idea, was to just be a better dog breeder.
Wow.
And that was before I even knew what biohacking was.
Okay.
And then when I started doing that, I started running into other people doing similar things, and then realized there's this whole group of people doing genetic engineering at home, and got involved with that. And it turns out that it's got a lot of much broader applications than just dogs.
And that is called biohacking. That's the point. So this is how you find out. Quindi ragazzi, ci sta dicendo che praticamente lui si è scontrato, tra virgolette, con questo mondo del biohacking per cercare di migliorare il suo lavoro di addestratore di cani. Questo è. Però vuoi fare... Do you wanna do some question?
Yes, I would like to introduce us to the biohacking community. I mean, who are the people in the biohacking community? Because from what I know, there are not PhDs or people from the mainstream science industry or science community. So what it looks like? Who are you guys?
So that's the interesting thing biohackers are everybody. There actually
Mm.
are some PhDs. There's a bunch of people who got PhDs in biology, and some of them are biology professors by day and biohackers by night. And there's a lot of people that used to work in industry or academia, kind of got fed up with it, or they found a better job opportunity in something else, but they still want to do it, or they just want to do the things that they care about, so they do it on their own. But there's also a bunch of people who come from like software backgrounds. There's a bunch of people who have genetic diseases and are trying to solve their own problems. There's a bunch of people who really love plants and just want to make crazy flowers. I mean, there's everybody.
That's great.
Wow.
So, praticamente Fra ha chiesto come funziona, come è composta questa biohacking community, e chiunque può far parte di questa biohacking community, e ognuno viene da background differenti, quindi ci sono sia persone che vengono da un ambito accademico che persone invece che vengono da tutt'altro, come per esempio lui, e si può utilizzare in tantissime cose. Questo ora gli chiederemo sicuramente. This is why my next question, sorry, I was continues my Italian speech. My next question is about what can you actually do with biohacking right now?
Right now, it depends on how well you're set up. But like, let's say sort of the most skilled people. Like I've got a buddy who made a tomato that's part cow. I've
A
there's
tomato
people
that is
part cow.
how?
He did it as an art project, really, but he put the cow myoglobin gene in a tomato,
Okay.
which is it's a muscle protein
Okay.
in a tomato.
So it's
So
a
I mean,
tomato made by protein, muscle protein. No, what was the end? The result of this
A
experiment?
strong tomato.
the result really, like, ideally would be a tomato that tastes a little bit like beef, maybe, but
Oh wow.
but probably not. It's probably just a slightly higher protein tomato. But like I said, he did it as an art project, just as a joke mostly.
Okay.
Just to see if he could. So it's like there is no end product.
That's crazy.
Wow, I never thought about this angle, like, using for bringing the meat characteristics, the meat feature to vegetables. That's enlightening.
Yeah, and
Quindi,
so go ahead.
yeah, I'm gonna translate briefly what we just said. Quindi ragazzi, fondamentalmente uno degli esperimenti che hanno fatto recentemente è utilizzare delle proteine delle mucche e impiantarle in un pomodoro, e questo come effetto è da una parte portare proteine animali in un vegetale, e dall'altra anche avere leggermente il sapore di carne, quindi una roba veramente fuori di melone. Wonderful. And Gian, do you have some question?
Yeah, it's still about this topic because I'm curious about. Okay, this is a funny thing, but I'm more interested in some useful thing, like for example, as you said before, in curing some dog disease, and I think, or curing some human disease. I don't know if you have some results that you achieved that are remarkable or interesting, or you're trying to achieve something like that.
So there's a few different things, like there's a open source gene therapy platform that I've been working on for about 4 years now.
Wow.
And so the idea is to make gene therapy more accessible. And so there's 2 or 3 different things that have come from that. Like there's one where basically some friends of mine took that as a platform and reverse engineered a multi-million-dollar gene therapy. And there's all kinds of stuff. Like there's some stuff that was covered in the documentary.
Yeah.
But then, like I've been able to genetically modify dog sperm. I just haven't been able to get the modified sperm to make puppies yet. And so when I get that, then modifying, genetically modifying animals is there. But for right now, like genetically modifying yeast and bacteria is super easy. I do that just as a regular chore. Like I've got some of that this weekend. So everybody can genetically modify bacteria. That's crazy easy. But higher organisms, plants, animals, humans, that's something that takes a little more practice. And there's probably only a handful of biohackers who are working on that. But there's also other people that are using microorganisms to produce things that address human things. Like, for example, there's a group of biohackers in California that are doing the open insulin project. So they're trying to make like a DIY open source insulin production system so that anybody can make insulin for humans.
Wow. So basically you don't have to buy it from pharmaceuticals.
Yeah. Or you could set up your own company and use instead of using the sort of traditional approach, that at least was patented. It's actually off patent now, but there's still complications with that. But basically you'll be able to just manufacture your own insulin using microbes. I mean, it's basically you'll be able to make insulin for about the amount of difficulty as it takes to make wine.
Wow.
Yeah, I actually don't know how you make insulin in general. So, but I guess it's something. It's something about you. So you can use this kind of procedures to make insulin on your own. That's the point. Okay.
Yeah, it's just tricky because it's a glycoprotein when you're trying to make it in, and it's got some insulin's a protein, but it's not like just an expressed protein. So if you're trying to express it in bacteria, for example, they don't quite have all the machinery, so you have to engineer the bacteria to be able to express it correctly. Mm-hmm. But human insulin is just a protein. So the way it's made now, like we used to extract it from the pancreases of pigs just by the thousands, right, to supply diabetics. But nowadays what we do is we have genetically modified bacteria that produce human insulin, and they just have big vats and they just produce it just like a brewery produces alcohol. They just grow it in huge vats and separate it out.
Yeah, so you can actually farm insulin from these bacteria. Quindi ragazzi, quello che ci sta dicendo è che il biohacking ha tantissime applicazioni, tra cui produrre l'insulina, che è una delle sostanze, diciamo, più richieste, soprattutto per chi ha malattie come il diabete. E questo tu oggi con il biohacking puoi produrre l'insulina con la stessa facilità con cui si produce magari il vino o la birra, quindi le fai, tra virgolette, farmare, come si dice in inglese, a questi batteri. Quindi veramente è un game changer per tantissime industrie. I would love to ask you about what's like the biggest result has been achieved from the biohacking community. I mean, I know it's not like a room with people in it, but
right.
From what what's the most crazy achievement is we achieved at the moment?
So it depends on your perspective. I would say honestly the most really useful achievement is actually more of a social thing. About getting people to look at science as something that they can do, and then pick that up, and then you give that time to run, and it'll start doing a lot of things. So I think as a point of sort of a beginning, I think that's probably the most important thing. But if you want to talk about something that's like technically interesting, like the most crazy thing was probably when Josiah successfully modified some of his skin to express a fluorescent protein from jellyfish. And then, detected that by RT-PCR. But, so for a little while he was part jellyfish.
Okay, can you explain that again?
Okay. So the craziest thing, I think the most useful thing is more getting people to think that, or sort of the idea of empowering people to use.
Yeah. Well, I got that. I didn't got the second one.
Okay. So the second one, Josiah actually used a virus to modify some of his skin cells to express a jellyfish protein. that normally is in jellyfish to make them green and fluorescent.
Okay.
And so he was able to modify his own cells to be green and fluorescent.
To be fair, okay.
But it was just as a small test, but it's pretty crazy that
it's
that's
crazy.
even
It's probably useless, but it's
it's
crazy.
totally useless. For like technically interesting, like on the genetics end, for a little while he was mostly human, a little bit jellyfish.
I love that.
Wow. So was made on human skin, this experiment?
Yeah, it was made on his arm.
On his arm.
Wow.
Okay, I translate a bit just to don't lose every information you just gave us. Quindi diceva che ci sono due principali, cioè Fra gli ha chiesto quali sono le cose più interessanti o comunque più assurde che sono state fatte nel biohacking. Dice la prima, la cosa più interessante è che dà la possibilità a tutti di avvicinarsi alla scienza, perché il biohacking è proprio che io non avevo capito, che è proprio quest'idea che chiunque può andare a fare ingegneria genetica. E la seconda, per esempio, ci faceva un esempio, un weird example che è stato fatto da un suo amico, se non ho capito male, che praticamente si è impiantato nella pelle del braccio una proteina o una roba del jellyfish che praticamente gli faceva diventare il braccio fosforescente per how long did it last, the effect?
It would probably be about 3 days before your immune system cleans it all up.
3 hours?
Yeah, about 3 days.
3 days. Okay.
Wow.
3 days per 3 giorni. That's crazy. That's crazy. Yeah, and I'm really curious about something practically. How does it work to edit a full arm, because do you like how does it work? Do you have to assume something? You have to put something in your...
So there's a bunch of different ways you can do that. So that's the thing about genetics is there's a bunch of tools in the toolbox and you have to pick the right tool for the right thing. So let's say you want to modify, just your skin, then the easiest way to do that is to use a virus and inject it under your skin, and it'll infect the skin cells. And if the virus has been engineered to carry your gene that you want it to deliver, it'll deliver that gene. Instead of delivering like normal virus genes, it'll deliver whatever your gene of interest is. That's the easiest way. But you can also do it with something called a plasmid, which is just a piece of DNA that's in a circle rather than in a virus. And you can do something I've been working on is a human artificial chromosome. And so I tested it on myself the test's been going for the last 3 years. Wow. But that's because the first year is blood samples, right? Of me testing sort of my normal levels for the hormone I'm trying to express. But the idea there is to actually engineer something that doesn't modify your genome, but sits next to it and is maintained in the cell. And that's pretty new. It's simple, and it avoids some of the problems with viruses because you can do it as just DNA, but they're difficult to make and they're difficult to get in your cells, and the results are not clear yet. Like my phenotype changed because the hormone that I'm trying to express is follistatin, which is a myostatin inhibitor, and in mice and even in human clinical trials for muscular dystrophy, they were able to show basically gains in strength and loss of body fat and things like that. Basically just their fitness went up. And so that's what I'm going for. The way I see it, doing all this lab work has sort of gotten me out of shape. So I want the lab work to get me back in shape, right?
Okay, that's crazy.
Sounds fair.
Yeah, exactly, right? So, and the way that works is a series of injections, right? But I'm targeting fat cells with that. So I'm actually injecting fat cells and recruiting those fat cells to produce this hormone for me and excrete it into my bloodstream, which then circulates around and affects everything.
Okay.
So it depends on what you're trying to do. Like if you're trying to modify your eye, you're going to have to do an injection into the eye. In the documentary, the boy Jackson got his retina modified by a virus. They had to do an injection in his eyeball.
Okay, wow. So it's if I got it, there are these two main way to do it. The first is with a sort of virus, right?
Mhm. Mhm.
Yeah, and the other
Yeah.
one is with what was the
So there's something called naked DNA transfection.
okay.
And so it's basically just these loops of DNA. Some of them are called plasmids, but you can also have other things like mini circles, artificial chromosomes, a bunch of different sort of structures
Okay,
that
is
you can use.
DNA with something around or is just DNA?
It can be just DNA, but usually there's a transfection reagent, or they'll use something called electroporation, where they basically help the DNA get into the cell. But you can just use just DNA. They actually have a technique called hydrodynamic delivery, where they really just put the DNA in salt water and inject it into tissue so hard and fast that just the water pressure shoves it into cells.
Wow.
So I mean, it's surprisingly not all that difficult to get foreign DNA in your body if you're willing to use a syringe and lots of DNA.
Yeah, it's pretty.
that,
So,
yeah, I'm gonna translate for
yeah. Go for
our
it.
guys. So, quindi ragazzi, stiamo cercando di capire un attimo come effettivamente puoi aggiungere caratteristiche, quindi biohackerarti il corpo. E uno degli strumenti sono i virus. Quindi, ad esempio, utilizzi un virus per veicolare queste nuove informazioni, perché come sapete o saprete appena ho finito la frase, il DNA è fatto di informazioni che poi fanno fare cose alle nostre cellule, al nostro corpo, quindi tu attraverso un virus puoi aggiungere informazioni anche senza intaccare quello che è il tuo DNA, quindi semplicemente come se fosse un add-on, e cambiare o aggiungere delle caratteristiche. Un altro modo è quello proprio di spingere proprio plasma, quindi informazioni, quindi parti di DNA nelle tue cellule attraverso un'iniezione. Quindi stavamo esplorando questo. Adesso gli chiederò come si fa, se è possibile, modificare tutto il DNA. David, I would like to ask you a question, because you know, when you use, I mean, maybe because I'm ignorant, but how can you like be precise in which cells you are targeting once you know you want to change something?
So there's different ways to do that. The easiest way is to just put it directly on top of those cells, because it really doesn't spread much. Like if you're using a virus, you can usually get more sort of spread. But if you're using like a plasmid, or especially if you're using something like electroporation. So let's say I wanted to modify like this little patch of cells. I would inject the DNA into that little patch. If I was using electroporation, I would then put 2 electrodes and shock that spot, and only the cells between the electrodes would be modified. Now, that wouldn't select a specific cell type. It would be skin cells and fat cells and stem cells and blood cells and all sorts of stuff. But if I say wanted to modify my liver, you know, there are different viruses, if I'm using viruses, that specifically target different kinds of cells. And also, I can do things like I can use different polymers, like PEI, for example, has a high affinity for lung cells. So there's different things like that, but also there's something called there's like cell type specific promoters. So obviously all your skin cells, your eyeball cells, your liver cells, your kidney cells, they all have the same DNA, right? But they don't all read
your DNA.
Yeah, exactly. Right. But they don't all act the same because all the genes aren't turned on in all the cells. So like your skin cells have the same genes as your liver cells, but they don't do the same things because your skin cells are only expressing skin cell genes and your liver cells are only expressing liver cell genes. Well, that's because there's a piece of genetic programming that tells liver cells what to do. So it's like, this is a liver cell specific promoter. So only in liver cells make this gene. So the other types of cells will ignore it, but liver cells will read it. Well, if I want my liver cells to make something, I'll take the gene out I'll make I'll have a virus and I'll load it up and I'll put a promoter that says, make this gene. And then I'll put my gene of interest, whatever it is, behind it. And then if a cell that's not a liver cell gets modified, it will say that's a liver cell promoter, don't make it. If a liver cell does, it'll say, oh, this is for me, and it'll make it. So there's actually genetic level programming you can do to make it turn on in specific cells.
Wow. So basically, I'm gonna translate for the guys because this is super interesting. Quindi ragazzi, fondamentalmente noi abbiamo il DNA, il nostro DNA è unico, però è chiaro che le cellule che
È
abbiamo
unico e uguale per noi in tutte le nostre cellule.
Esatto, quindi è come se tutte le cellule hanno questa quantità di informazioni, però la differenza è che alcune cellule lo esprimono, quindi ad esempio le tue cellule quando diventano cellule del fegato si attivano solo una tipologia di geni, mentre quando ad esempio diventano cellule della pelle si attivano altri geni. È come dire, tu scarichi tutto il codice di un software, solo che gli dici ok, se va su, che ti posso dire, se lo apri da cellulare attiva solo queste parti di codice, se lo apri da desktop attiva solo queste altre parti di codice, e nel nostro corpo funziona esattamente così. Wow, this is actually beautiful.
And I have a question on that. Is this a piece of information that tell which gene to activate and in which case is inside the DNA itself, right?
Yeah.
Okay.
Yeah. So you can try to control which cells you modify, but you can also control which cells the genes are active in. You could even make it so that you had a package of several genes that different ones would be on in different cells, depending on the cell type. So
you can do that with biohacking.
Yeah. So there's different I'm trying to think of a non-technical way to say this. So there's ways to sort of program genes to turn on and off in certain situations. You can even use environmental promoters. So for example, there are promoters that only turn on when they're exposed to certain sugars or things like caffeine or tetracycline. So you can actually modify cells and then have them not do anything and then turn those genes on by taking a certain chemical that those genes specifically respond to. Like you could take tetracycline and turn a gene on that you've modified, and then it would run and do whatever you programmed it to do. And then when the tetracycline left your system, it would turn off again.
Oh, wow. So you can actually like pre-program it to be triggered from some external event. Like you get some caffeine and then that's going to be the trigger.
Yeah. And you can do things with testosterone. I mean, there's all kinds of triggers that turn genes on and off in your body. That's just part of how your body works. But it's also...
So just to make, a silly example, you can actually become green only when you get mad.
Yeah, theoretically, yeah. It would just be slow, right? It would just be slow. But also, there's other things. Like I have bacteria that glow, that change color when they're exposed to light.
Okay.
So they actually can sense light and change color. And that's all programmed in DNA by people, And
yeah, like a software.
Yeah, exactly. And that's the thing. It's becoming more and more like software. And you can even do like control loops. So you have an inducible promoter, and then you have a gene, and then on the end of that you have the promoter again. So as soon as you activate it, or you have the inducer. So as soon as you activate it by supplying an external thing or whatever happens, the gene gets made, and also this gets activated, which keeps it activated. So you have a positive feedback loop. And
okay, so you can actually trigger once, and then it's gonna be like a loop.
Yeah, or you can have it where, and then you can put something in there as well that can turn it back off again. So you can take something else.
When to start, when to turn off, that's the point.
Yeah.
Fra, fai un piccolo recap in Italian, please.
Allora ragazzi, stavamo cercando di capire un po' quali altre, possibilità hai per programmarti, e una delle robe fighissime che ci stava raccontando è che fondamentalmente tu puoi decidere qual è il trigger per far partire una modifica. Quindi ad esempio tu puoi decidere che la tua pelle diventa verde solo quando viene colpita dalla luce, quindi puoi avere un trigger. Un trigger è come si traduce già in italiano? Un trigger,
un evento scatenante.
Esatto, un evento scatenante che determina quei geni di attivarsi. Quindi ad esempio ogni volta che bevi caffeina diventi verde, ok? Perché l'hai programmato per essere
Tu l'avevi
sensibile a
detto più bello,
quell'evento.
ogni volta che ti arrabbi diventi verde, come Hulk.
Esatto, perché quando ti arrabbi ti vengono iniettate adesso io non sono un tecnico, però cambia comunque la composizione biochimica del tuo corpo, quindi se lo programmi proprio su quello, l'innesco, potresti potenzialmente diventare verde. E l'altra cosa interessante è che oltre a poterlo fare, quindi programmandolo per un innesco, lo puoi fare anche in modo che abbia un loop di feedback, quindi una volta che è triggerato continua ad esistere, quindi continua ad agire.
And you
Oppure
can also
dove
do things
iniziare,
like,
dove finire. Sorry, David. Go on.
you can also do things like that's how a lot of kill switches work. So, like, say you wanted to modify T cells to be able to kill, like, you've got a cancer that's avoiding your immune system, so you want to modify your immune system to kill that cancer, and that's actually something they're doing a lot of with CAR T therapy and stuff. But say you wanted to add a kill switch, you could have it tetracycline inducible, so that if the modified T cells go crazy and start attacking your body, and not just your cancer, you take tetracycline and it activates a gene that kills the cell. So only the modified cells would die because they've been programmed to.
So you can actually be hyper precise in these things.
Yeah, and you can
And
kill all the
you're really answering just a question that arrived here in the chat that I don't know, probably you cannot see them, but they're saying could it be risky? And you just said that you can program the cell to stop if something bad happen or to destroy itself.
Yeah.
Okay, all the edited cells.
Yeah, so you take a drug that would turn on the kill gene and then it would kill the cell.
Okay.
Cioè, quindi fondamentalmente se ad esempio tu ti stai riprogrammando il sistema immunitario per uccidere delle cellule cancerogene, però magari hai fatto qualche errore e sta iniziando a fare danni anche in altre parti, tu potresti assumere un altro po' di DNA o comunque biohackerarti, per usare un termine un po' più generico senza entrare nel dettaglio, e fare in modo che questa nuova assunzione di cellule di DNA vada a targetizzare solamente le cellule modificate in prima istanza, quindi vai a risolvere quel problema, perché effettivamente puoi programmarlo proprio in modo molto molto specifico. Quindi questa è una roba fuori di melone, ragazzi.
David, is there any like actual real result in cancer fighting, or for example I heard about in the Netflix documentary about HIV, is there any result on this?
Not in terms of like a person cured of HIV. There's only been like 2 people ever, but there were results in vitro. So for example, the antibody that we made actually does bind to the HIV virus, and so we were able to prove that, but getting enough of it to neutralize the virus is a whole different thing. And that's really what my open source gene therapy project's been about, is what's the bottom, like what's the cheapest, easiest way to make a full body modification, because that's orders of magnitude more difficult than modifying a small number of cells in a small place.
So let me understand it better. Your gene therapy open source gene therapy project is like a database that everybody can read and enrich. How does it work?
Well, my idea is like, okay, my YouTube channel, right? So I'm basically just developing a set of protocols to do gene therapy for yourself that's as cheap and easy as possible, and I'm covering how to do all the steps from I don't know what I'm doing to I just did gene therapy on myself, and how to build all the things and find all the things and design everything. And I'm trying to sort of make a platform so that you can easily take that platform, pop out the gene that I'm using, put your own gene of interest in there, and then just run the protocol and then have whatever the modification is. So like my thing may be built on making me more muscular, but somebody else's thing may be curing some horrible disease that's affecting them, you know. And like there's even people that have contacted me who have muscular dystrophy who want to do exactly the same thing. And so the idea is to create a foundation on which other biohackers can build things that address other things, and then just let it go into the world, so people can just take it from whoever's got it, modify it to do whatever they're interested in, use it, share it, and then just have a sort of decentralized network of people working these problems on their own.
It's wonderful. It's amazing.
Yeah, this is beautiful. As I told you the first time I wrote you on Facebook, I'm like super happy, and you're doing a great service for the humanity, because you guys are pioneers, and trying to find out this new technology and applying it every day, and it's beautiful. I'm gonna translate it for our folks, because this is deserve to be translated. Quindi ragazzi, fondamentalmente loro stanno lavorando a questa piattaforma open source in modo che possano mettere online, comunque condividere tutte le a parte le scoperte che fanno, ma proprio dare questi strumenti a chiunque. Quindi se tu hai una necessità puoi fare, adesso lo traduco diciamo in modo anche abbastanza superficiale, però puoi anche se non hai tutto il lavoro che hanno fatto loro, se non lo hai mai fatto, non hai tutte le competenze, però c'è un protocollo in cui grazie a questa piattaforma tu puoi fare delle, tra virgolette, delle richieste in base agli obiettivi che hai. Quindi magari il tuo obiettivo può essere aumentare la massa muscolare, piuttosto che uccidere un certo tipo di cellule cancerogene, e poterlo fare autonomamente senza dover andare in chissà che grande istituto, perché fondamentalmente è tutto open source e online.
Praticamente, no, e volevo tradurre pure la cosa che diceva prima. Praticamente l'ha chiamato un progetto open source, che vuol dire aperto a tutti, di terapia genetica, in cui è come se fosse un progetto di codice di software, in cui ognuno mette, che ne so, tipo per fare il form, per fare la landing page questo è il codice che devi utilizzare, per fare più muscoli devi fare questa procedura, e chiunque può, diciamo, arricchire questo lavoro decentralizzato fatto da più persone. E la cosa che diceva prima, che mi avevate pure chiesto in chat su HIV, cancer e queste cose qui, dice che comunque ci stanno lavorando in diversi, non è mai stato curato nessuno fino ad oggi, ma sono stati ottenuti dei risultati in velcro, come si dice, sicuramente non è velcro, in provetta, diciamo.
Sì, esatto.
Sì.
Esatto. So one of my questions, David, was
vitro.
was about your point of view about the open science, but from what you're saying, you're absolutely down with it. Like, you embrace it.
Yeah, because I think.
Please.
I was going to say, because I think it's difficult. I like, there's a bunch of competing interests when you're a pharmaceutical company, right? Like, you're trying to cure a disease and satisfy your customers, but you're also trying to make money and satisfy your shareholders and obey the laws and all these sorts of things. So there's a bunch of different knobs, but with completely open source science, the only motivation is just to fix the disease, because you're not going to make money at it. You're not going to piss off your shareholders if you say, well, this didn't work, it was bullshit, So it's nice that it can sort of be science in its purest form. So I like that.
It's wonderful. I translate this for the guys. Il concetto, ragazzi, che diceva di questo progetto, diciamo, open source, perché Fra gli ha chiesto che ne pensi della scienza aperta, non so come si traduce, però l'idea che tutti quanti possano contribuire, diciamo, alla ricerca scientifica. E quello che diceva giustamente David è che comunque tanta ricerca viene fatta e finanziata comunque da conglomerati o comunque da grandi aziende che hanno uno scopo che oltre a curare le malattie è anche quello del profitto, e invece in questo modo, diciamo, non c'è quella parte lì di interesse, ma c'è solamente la parte di interesse di curare le malattie e di aiutarsi a vicenda nel creare questo patrimonio di informazioni che può essere utile a tutti senza uno scopo economico dietro.
Yeah, I have a question related to what we were just talking about, open science. So what do you think about the do-it-yourself ideology? I mean, there is a chance you can create something that is It's a hard word. It's a hard word. It's irretrievably, like you cannot come back from some changes, and you're gonna spread it, in the world.
Like COVID.
So, right. So a few things on that, right? First of all, it's very, very difficult to make new things, right? So modifying something that isn't that hard. But say you wanted to make something that has never been, like, okay, we're not, like we're not one, like, okay, so I work a lot with E. coli, right? Lab strains of E. coli. We're not one mutation away from that E. coli becoming a terrible thing, right? If we were, we would all be dead now, because that stuff mutates all the time. Like, people don't realize quite how frequently things mutate. But generally speaking, biohackers don't work with pathogens, right? I don't know any biohackers working with pathogens. Well, one. but
Danger enough.
Okay, but that's herpes, right? So everybody's already got herpes. It's like 90% of the human population has herpes anyway.
Oh, okay.
Fair enough.
So, but typically, like, novel zoonotic zoonotic pathogens is not something you see in biohackers working with. And so that's not a big danger, but also most of the things ever tried in biology just don't work, at least not the first time. So the way you make something work is you have an idea, you make a design, you test it. Like, okay, my gene therapy project, I'm on version 7 because the first 4 didn't work at all. And then 5 works in vitro, but has problems. So I'm on version 7. So what you would have to do if you wanted to make something terrible, like, you're not going to make something like coronavirus accidentally. But if you wanted to make something terrible, you're a mad scientist, you would have to make it, and then you'd have to test it, and then you'd have to figure out why it didn't work, which means you need to collect health data from your test subject, and then you need to do more testing, and then, like, to try and get an idea of how it spreads to a population and all that data, so that you can do iterations and improve the design. You need a bunch of people to experiment on. So you need like a prison population.
Yeah, you need like a Nazi scenario.
Yeah, exactly. So like a rogue state, like I could see North Korea working on something like that. I could see like Stalin's Russia working on something like that. If you had a totalitarian state, or even like a terrorist organization that was well funded and had prisoners like ISIS, you could probably do something like that. But one person in their garage is not going to have the resources to do something like that successfully.
Yeah, so basically having like a decentralized and open knowledge is gonna somehow prevent that, because you need like a monolithic situation to being able to test it until you get like a decent version of it.
Right. Because like, okay. I mean, you think about like the flu, like say you wanted to make a terrible super flu. It's not one random mutation that's going to do that, because the flu mutates all the time. And sometimes it's worse and sometimes it's not, but flus mutate constantly. So even if I were stupid enough to just be cooking up some flu virus in my lab, first of all, the most likely person to get sick would be me.
Yeah.
But also,
fair enough.
But also, even if I randomly mutated it or mutated it by design, it probably wouldn't do anything. And then who would I test it on to see if it works? And so I'd need like a whole like prison of people, that I could test on and then take blood samples of, and then so you need at least a prison to experiment on. So
yeah,
if you're looking for,
you just cannot like spread in the wild. You need actually to monitor it, to monitor them, to gather data about it.
Yeah, because if you just like infected your neighbor and your neighbor didn't die, well, what mistake did you make? What changes do you need to make? Why didn't he die? So now you need to like, hey neighbor, I need a blood sample. And can you get it? I have some questions about why you're alive. And it gets suspicious really fast.
Ok, do you want to translate, Fra? And then we...
Sì, allora ragazzi, stavamo esplorando un attimo un po' che è uscito dalle vostre domande, cioè perché o quant'è il pericolo di, diciamo, anche se uno agisce in buona fede, arrivare a creare qualcosa dannoso, per assurdo una roba tipo il Covid. Ed effettivamente una cosa interessante che ci sta raccontando David è che comunque cioè non è facile arrivare ad un risultato, quindi arrivare a sviluppare qualcosa che funzioni realmente, non solo in vitro, ma proprio nel mondo esterno, considerate tutte gli imprevisti e le dinamiche che ci sono. Tant'è che dice: è più probabile che questa roba succede in paesi tipo Corea del Nord piuttosto che Russia, in cui hanno il potere e anche magari il potere di avere delle persone, magari prigionieri, su cui testare queste cose, monitorarli continuamente, quindi imparare e capire dove stanno sbagliando, rispetto a un singolo scienziato pazzo che fa fare quella mutazione incredibile a un virus o a qualcosa e fa i danni nel mondo. Quindi il fatto è che proprio, cioè, per arrivare a un risultato servono tanti dati e serve soprattutto la collaborazione libera o forzata delle persone per arrivare ad un
Per
risultato
fare
del
dei
genere.
test, per vedere se una cosa funziona o non funziona. There is something that I'm pondering about the thing that you said, that is biohacking is the thing that everybody can biohacker, can genetically engineer ourselves, or biology in general. But isn't any technology gap or any money gap, investment gap? I mean, what is the difference between a pool of engineer inside a lab, a really expensive lab, and, for example, me and you in your lab?
Yeah. So my lab is I wish I could show you, but it would be all crazy. There's too many cords. But
Okay.
so there's a big difference, honestly. Like if you look at something like the genetic engineering lab at like UC Davies or something, they have much better tools than me. Almost all my equipment is used or homemade. So I've built a lot of my equipment, and you know, there's some things like, obviously, like, you know, beakers are beakers. They're the same everywhere, you know.
Exactly.
But and like my PCR machine, they're not that expensive machines, but they manufacture DNA for you. And like I got a used centrifuge from a university on like a government surplus website. So there's things you can do, but you're not going to generally have the top of the line and a staff of people. And like I don't have a biosafety cabinet. I don't have a -80 freezer. I don't have a lot of the nice tools.
Okay.
And so that makes things difficult and slow. And so just having a lot of funding and having a staff, you know, that can work 7 days a week, all day, every day,
helps.
makes a big difference. Yeah, it does.
Okay.
And also you have things like there's some restrictions in what you can purchase, right? So like I can't just go, like if I wanted to buy like smallpox genes from a DNA synthesis company, they wouldn't sell them to me. You know, you have to be certain organizations to get those things, which is good. We don't want just everybody to have smallpox genes. And so, you know, then there's things that are overly restrictive. Like sometimes you can't just get like antibiotics that you need for selecting bacteria. And so you have to kind of get weird roundabout ways to get supplies. And those things slow you down, and you know, all the stuff's overpriced, so that also slows you down. But I think in terms of what you can do pretty much all the same things. It just takes more time. And then some things like I know a bunch of biohackers trying to make a vaccine for COVID, and I know a bunch of them trying to make you know, test kits and things like that for COVID. But the problem is they'll never be able to compete with the hundreds or thousands of giant labs producing stuff right now. So they'll always be behind. So I think biohacking shines most when it's addressing problems nobody else is, rather than problems everybody else is trying to solve.
Or
So
perhaps
you
the
can
point...
compete on the long tail, on the problems in the long tail.
That's right. And perhaps the other cool thing would be if an expensive lab with a lot of teams can solve an issue and release an open source procedure to do that. Everybody with a some biohacking, I don't want to say background, but skills. And this is where I want to move as a topic. But everybody with some skills can implement himself. That's the point. That could be a point. A short translation for our friends. Ragazzi, praticamente stavamo chiedendo quali sono poi le differenze, se il biohacking vuole rendere possibile a tutti di utilizzare questi strumenti di ingegneria genetica, qual è la differenza tra dei laboratori costosi. Effettivamente ci sono tante differenze di strumentazione, però senza andare nello specifico, il concetto è che praticamente i risultati che puoi ottenere possono essere gli stessi, ma ci vuole molto più tempo, e poi devi comprare la roba usata, piuttosto che alcune cose non le vendono perché le vendono solo a alcuni tipi di aziende. Ok, and now my question is, if I want to be a biohacker, what should I do? Where to start? What I have to buy? What I have to study?
So that's a question I get a lot. And in fact, I'm making a whole YouTube video on answering that question.
Okay.
But the basic idea, or the big piece of advice that I give people is you have to have a project. You have to have a goal. Because I see a lot of people that are like, I want to become a biohacker. But that's kind of like saying, I want to sail. And so you just row out onto the ocean and you're not going anywhere. You have no destination. You're just out there. And so you don't get very far, you know? So my thing is, it's such a big space. I mean, it's like the ocean that you could go 1,000 different directions and nobody does it all. Like I know nothing. Well, I know like just the theoretical stuff about genetic engineering plants, but it's a whole different universe over there in plants. I focus on animals. And so, and then there's the fungus guys. It's a whole different thing, right? So if you're trying to get into biohacking, I recommend picking a project, something that you think you probably can't really do. An ambitious goal, I think, gives you a direction to follow. And then you start thinking, okay, well, I'm going to genetically engineer a dog. That was the goal I started with. So, okay, that means I need to be able to modify sperm. That means I need to be able to do these things. That means I need to be able to make DNA. That means I need to be able to culture bacteria. That means I need to be able to do all these different things. And so you kind of, once you have a destination and a origin point, everything in between kind of fills itself in. But there are tools now that do help. Like the Odin has online classes that help, that are kind of designed around the things that most people have to do, like PCR, electrophoresis, that sort of stuff. But they don't get into the specific things. Like there's no class for doing sperm-mediated gene transfer, because that's a very specific thing for a very specific application. But then there's places, again, like the Odin, where you can buy like supplies and stuff, like antibiotics and growth media and lab strains of bacteria and that sort of thing. But you can also get a lot of stuff on eBay or Amazon. And there's a bunch of different sort of videos with different biohackers and their different lab setups, but they're all built around different goals. You know.
And how did you start?
How did I start? At the very beginning, like I said, I was interested in doing genetic modification of dogs. So,
but did you have a background? Did you have a background?
No, all my genetics knowledge at that time was from being a dog breeder.
I love that. Okay.
So, you know, I did a lot of reading, and there's places you can go, like there's Google Scholar, so you can just go scholar.google, and you can Google search all the scientific papers ever published. So if it's in Cell or Nature or Science or any of those things, you can read the papers that are intended for scientists to read, so you can really get the details. And the problem is most of them are behind paywalls, because like Nature is a paid publication. But there's a hacker website called Sci-Hub. It's like sci-hub.tw. That's a hacker website where they have hacked all of the scientific publication and made all the papers free. So what you do is you go to Nature and you find the paper you want to read by some scientist at, say, you know, University of Chicago or something, and you want to read his paper, but it's behind a paywall. They want you to pay $39.95 to read the paper. You take the address, put it into Sci-Hub, read it for free because of the hackers.
Okay.
So there's things like that give you a lot of access to information that you can learn. And then there's also things like there's a surprising amount of stuff on YouTube, even sometimes by the manufacturer. So a lot of stuff is kits. Like let me find it. Well, I guess it doesn't matter, but a lot of stuff comes in kits, right? So like I have kits for extracting DNA. So for example,
let us see it. In the meantime, I can give a translation.
Yeah, I'm gonna translate in the meantime. Quindi ragazzi, gli abbiamo chiesto un po' come se uno volesse diventare un biohacker, da dove iniziare piuttosto che da dove ha iniziato lui, e fondamentalmente è tutto online, perché tu online puoi trovare sia informazioni da chi produce proprio gli strumenti che poi vengono utilizzati, puoi trovare articoli scientifici che vengono chiamati white papers, anche se molti sono a pagamento, però c'è il lavoro degli hacker, quelli digitali, che hanno creato diverse piattaforme per farteli leggere gratis, quindi veramente ci sono tutti i layer di informazione online, quindi puoi arrivare veramente nel profondo, tipo l'ultima ricerca e scoperta fatta dai migliori laboratori e i migliori scienziati del mondo, perché comunque esistono queste pubblicazioni scientifiche. E poi diceva che su YouTube c'è una marea di roba che non avete idea.
We get
Yeah.
Light language question. Did you call hackers digital pirates?
No, we call it hackers.
Okay. I thought I heard the other. Like that's
sometimes we call it informatic pirate, like in a technical way. Informatic pirates, pirati informatici. Yeah.
So like this is a DNA extraction kit, right? So these are commercial kits.
Okay.
So like it's let's see if I can. It's chemicals and like silica columns and stuff. But it comes with instructions, and the manufacturers all have videos on YouTube showing you exactly how to use their product.
Okay.
So I mean, and these come in different sizes for different applications, and all the little things like, oh, I need to extract and purify RNA. Well, you can just get the kit for that. Oh, I need to, whatever you want to do. There's kits for just about everything. It's all been kitified.
You buy it on eBay or Amazon, place like that?
Yeah.
Wow. Okay.
Yeah, like I have a GigaPrep kit, which is about 16 times bigger. It's 2 giant boxes, right? It's designed to take huge amounts of DNA. That one takes a very small amount, collects a small amount of DNA. That one collects.
But how does it work practically?
So really, it's like it's got a bunch of chemicals. So you grow up some bacteria. Usually, you'll make like you'll start with like a petri dish, right? And then you'll have like a broth. So you'll have them in a flask with liquid. You'll add the bacteria in there. They'll grow up, and the bacteria have been modified to carry the DNA that you want. You've added that DNA to them, then you grow them up, and every time they reproduce, they're copying your DNA. And so then you use chemicals to destroy the bacteria and extract and purify the DNA by sticking the DNA to a silica column, washing all the crap out of it, like protein and all the bacteria bits. And then you just sort of make bacteria inside soup, and purify out the DNA and just the part of the DNA
that you want.
Get rid of the rest of it and then wash it out, and you end up with a tiny little tube about this big, full of a little bit of water with purified DNA in it.
So you have actually pure DNA there. Inside water.
Yeah, and you can actually dry it all the way down till it's just DNA, not even water. It's in which case it's a solid. It's like a very, very, very small amount of powder.
It's really interesting. Do you want to translate? It's a really long. I can say in Italian some long story short. But,
sì, praticamente ci stava raccontando un po' come funziona arrivare ad avere tramite questi kit o comunque tramite questi strumenti di lavorazione del DNA, e fondamentalmente tu utilizzi dei batteri e li fai crescere come in vitro, quindi come si fa con i batteri, li fai crescere, li fai moltiplicare, quindi questi batteri portano il DNA che tu hai scelto, nel senso che tu prima glielo... David, how do you start to implement the DNA, to inject the DNA you want in bacteria in the first place?
So that's chemistry. So what you do is you grow bacteria up, very similar to that. And the protocol is actually really easy. So calcium chloride is sort of the magic ingredient. But basically, all you do is you take the bacteria, you grow them up in like it's LB broth, which is basically think of it like chicken soup almost. So you just grow them up in broth, and then when you collect the bacteria, you just put them in a centrifuge, spin them around. The bacteria are heavy; they go to the bottom. You extract off the stuff. You put them in a solution of calcium chloride, which changes the polarization of their membranes. So like they have a membrane, right? And DNA is negatively charged. Cell membranes are negatively charged, so they can't get through very easily. But the calcium chloride is positively charged and neutralizes those charges and lets some of the DNA get through. And then you just but you have to keep them cold when this happens. So you get them really, really cold. You do that, and then you do something called heat shock. You put them in there with the DNA and the calcium chloride. You put them in a slightly warm environment. It's like 40 degrees it's like 42 degrees in Celsius. And then for like 30 seconds. And then that heat shock helps damage their membranes just enough for some of that DNA to slide through a little bit better. And then you just plate them out. And then they start growing up with the modifications.
Okay, that's great, and I'm gonna translate really easy. Let me say, ragazzi, è un processo chimico, quindi ti danno questi strumenti e adesso è complicato pure da ripetere, però...
Esatto, però in massima sintesi, una volta che tu, diciamo, abbassi le difese delle membrane di questi batteri, gli puoi mettere dentro il DNA che vuoi tu, poi li fai crescere e poi fai tutto un altro processo chimico per isolare il DNA da tutto il resto. Ok, easy peasy.
I have a YouTube video that explains it all in
ok, potete trovare tutto comunque cioè le cose tecniche se volete approfondire gli aspetti tecnici sul suo canale YouTube. David, I have a question. How much does a kit to start cost or a biohacking kit cost average?
So it depends on what you want to do.
So of course.
Let's say like okay, like that kit to extract DNA. Like it doesn't really do biohacking. It just purifies DNA from bacteria.
Okay.
But by itself, that costs about $50. But you can get but it does 50 reactions, right? So it's about $1 a reaction.
Okay.
And you can go on to like again the Odin, and you can get like a whole lab setup for I don't remember what it costs, but a few $100s. And then you can go.
Okay, not so much.
Yeah, or you can, if you can like price out things very specifically or build your own stuff. Like my first shaker I built out of probably like $12 worth of stuff. And so it depends on what stuff you need and also how lucky you are. Like I bought a spectrophotometer one time on eBay for $1.98.
Wow.
Because the company that had it was selling a bunch of medical and laboratory equipment in bulk, a bunch of used stuff. And they were just charging one flat price, $198 for everything. And they put the decimal in the wrong place on one of them, and it was $1.98.
So they just wanted to get rid of that stuff.
Yeah, so I think they just instead of putting 198.00, they just put 1.98. And so I was like, $1.98 per spectrophotometer doesn't even matter if it works. So bam. So my spec cost almost nothing.
Ok, a quick translation for the guys. Praticamente ho chiesto quanto costa prendere un primo kit o i kit di cui ci stava parlando, tipo quello che ci ha fatto vedere costa sui $50 e ti fa fare tipo 50 reazioni, quindi €1 a reazione. E poi dice che ci sono cose che ti puoi anche costruire da solo, altre che puoi trovare, comunque tipo un intero lab, un intero laboratorio anche con qualche centinaio di euro lo puoi mettere su.
Te la cavi, esatto.
Sì.
David, I have a question. When you read about biohacking, usually it's related to this ideology called transhumanism, so making superhumans. And when they talk about that, it's like they usually speak about achieving super intellect or immortality. Let's put in this word. So what's your point of view in this on this?
So I wouldn't consider myself to be a transhumanist. though that's sort of a sticky point of philosophy. Like, I don't hold it against anybody trying to improve themselves. And I definitely think the human race could use improvement. And I'm not against the idea. Like, for example, a lot of people thought it was crazy that in China last year, Dr. He Zhonghui, I think is his name, genetically modified human babies to make them immune to HIV, basically. And at the time, everybody thought, this is crazy. We shouldn't be modifying humans. This is irresponsible and wrong. And he actually went to prison in China.
Wow.
Did it work?
Yeah, it worked.
Oh.
So, but my question today, after coronavirus has spread around the world, do we still feel so strongly that modifying humans to make them virus resistant is a bad thing?
That's a good question.
Yeah, that's a great question, actually.
So,
Okay.
One of the things I want to do with my dogs is modify them to be born immune to all the major infectious diseases too, like parvovirus. And I would love to see humans that way. So making humans that are healthier, smarter, live longer would be good. The issue is availability to me. That's the biggest issue is if it costs $1 billion to have like a super baby, most people won't get it. It'll be a handful of people. And like some of my experiments, like with my gene therapy, I tested in mice originally, and I let those mice grow their whole life. And so the mice that I modified lived 14% longer.
Wow.
The most modified ones. I had a litter of mice, and I modified some of them. And all the unmodified mice died of old age. And the only ones left were the modified ones. And from the lowest dose to the highest dose is when they died of old age. So the
It
most
worked,
modified,
actually.
it worked. Yeah.
Wow. So what kind of result you can imagine in the future for humans in terms of longevity?
In terms of longevity, I mean, I think what we've been able to do with mice is pretty impressive. We've got mice that live like 5 times longer than normal, but cancer is a big problem. So even if you modified humans to be able to like have healthier hearts and those sorts of things, there's some things we could probably do immediately that would give you 20% more longevity, things like that, because they basically mirror things like caloric restriction, at least on a metabolic level. And those have been proven to extend longevity. But I would say within the next, say, few generations, we could probably see maybe a 2x increase if we really embrace these technologies. If we don't, it won't change much at all. But I don't see like living forever in the immediate future. But then that's kind of one of the sort of more transhumanist ideas that people have is where will we get in 200 years? So like if you could live to be 190 years old, maybe you live long enough that they've made so much improvement that you could get there where you get the good stuff, where you live to be 500. And then you get, by the time we get there, you get the even better stuff.
Yeah, exactly.
1,000.
Wow. So I'm gonna translate it because it's fucking crazy, I love it. Quindi ragazzi, stiamo parlando un attimo di che risultati si possono ottenere, come avete scritto qui in chat, dagli esperimenti sui topi che ha fatto direttamente lui, è riuscito anche ad avere un 5x in the mice?
Yeah, something like that. It's like,
ok.
In some experiments.
In alcuni esperimenti sono riusciti addirittura a prolungare la vita dei topi per 5 volte più lunga rispetto alla durata standard, quindi è come dire se un cristiano campa di media 80 anni, 80 per 5 sono riusciti con i topi. E la cosa incredibile è che effettivamente uno degli aspetti interessanti è che se si riescono a fare dei passini in questa direzione, non è che devi arrivare all'immortalità in un colpo solo, perché basta arrivare a magari a campare 150 anni e nel frattempo gli avanzamenti tecnologici di gene editing ti portano a viverne altri 100, altri 200, altri 300 e nel frattempo è così a cascata. Questa è tutta un'idea e un'ideologia che si chiama transumanismo, che dice transumanesimo, che dice proprio che attraverso il gene editing, attraverso proprio, diciamo, un'applicazione profonda delle dinamiche biologiche, l'essere umano può diventare un superuomo e addirittura ambire all'immortalità. David, what's your point of view about, let's put in these words, biological immortality? Like, what does it mean?
I don't know if like true immortality really is possible. I mean, or let me put it this way. I don't think it's possible with the humans that are alive today. Not without something really extreme, but I think it's possible to engineer a human in the future that would be, because like one of the major things is cancer. Even if you could turn off like the aging process itself, which is something a lot of longevity people focus on, you still are going to get cancer at some point. And so you have to cure cancer first, and you also have to cure Alzheimer's and heart disease and all these other things that you see associated with aging, and especially cancer, because let's say you live to be 1,000. Well, that means your cells have cycled over and over and over again. You've accumulated a huge number of mutations. So you need something that protects your cells against cancer. And if you engineer a single cell, like an egg cell, to be super cancer resistant, like the way elephants are or some other animals, you could grow up a whole human who all their cells were modified. But if you wanted to modify an adult, modifying even a huge number of cells, like 20% of their cells, wouldn't do it. You would just develop cancer in some other part of your body, right?
Okay.
So you would have to be able to modify all of you. And so I think we can create a generation of humans that could live forever. But I don't think we'll be able to just get it unless there's some really impressive changes in biotech in the next few years. Because the issue is it's all delivery. It's like how, even if you can program it to live forever, how do you deliver that to every cell in the body? And so that's the challenge.
Yeah, so it's gonna be easier with new people, with new entities. Okay.
But I have a question about that. How much of the genetic engineer you can do on yourself or on a human being is going to be irritated to his son or?
Basically none. So like, say I modify, like, okay, I modified some of my fat cells, right?
Mm-hmm.
But that won't affect the cells that produce sperm, right? Mm-hmm. So there's actually a technique called testes-mediated gene transfer. So if you wanted to do that, you could modify the cells that produce sperm by injecting your testicles with like a virus to modify those cells. And then you would produce modified sperm, but it would still be a minority. So then you'd have to probably have a bunch of children to have one of them be born that way.
Okay.
So you'd have to do it on purpose, basically. It wouldn't just accidentally pass, because everything we can really do right now modifies a small number of cells in a local area.
Ok. Quindi praticamente I do just a quick recap. Praticamente il punto è che per ora dice, anche se uno provasse a iniettare l'immortalità, quindi la longevità, l'anti-aging nelle cellule, c'è comunque il problema di malattie come il cancro principalmente, che andrebbe a prendere comunque, anche se fai una soluzione contro il cancro oggi non siamo in grado di modificare il 100% delle nostre cellule, ma un 20% rimarrebbe sempre a rischio. E questo è un problema che oggi
esatto, quindi diciamo in quest'ottica sarebbe più facile creare nuove generazioni che proprio dall'inizio sono resistenti al cancro o a tutta una serie di malattie o dinamiche genetiche rispetto di modificare un essere umano adulto.
That said, I do think genetic modification could make the people who are alive today live longer than they would have without.
But in your opinion, it's quite hard from where we are right now to being able to change like 100% of adult human being cells.
Right. Unless you do something extreme like clone yourself, grow it up to an adult, cut your head off, and pop it on.
Fair enough.
You said before that you are working on prevent or cure genetically the disease of your dogs, right? And how far are you in this research?
So I've been doing it for years, and I can successfully modify sperm.
Okay.
The issue that I've been having is trying to get those sperm to actually make puppies. And so far, all of my breedings have resulted in no pregnancy, no puppy. And I think I know why. I was talking to a genetic engineer at UC Davies who gave me a good tip that I think might help me. But basically, there's a part of the sperm that's called the acrosome. It's like this extra membrane on the front, and it's supposed to help the sperm get through the zona. So the zona is like a protective forest of protein and sugar around an egg cell, right? And so the zona the acrosome contains enzymes that digest their way to the egg. So if in the process of modifying the sperm, I accidentally caused the acrosomes to activate prematurely, which is very easy if the pH is a little off, and it varies from species to species, or if there's too much calcium or too much magnesium, this can happen. And I think that's what's happening. But basically, I have a stain now, this stuff that just came in, that I'll be able to visualize the acrosome because it'll selectively stick to the acrosomal membrane. So basically, I'll be able to modify the sperm using the same protocol I've been working on, because it works in pigs, but to get it to work in dogs is a transition, right? So I'm trying to develop a protocol where it works in a new species. And if I'm causing the acrosome to rupture prematurely, I'll be able to see that with this stain. So if that's right, if the acrosome is the problem, and if I can see it, then I can modify the protocol until I get genetic modification, and I can see that under the microscope by using fluorescently labeled DNA, and then also be able to see that the acrosome's intact. I might be really close, because if that's my problem, then I'll have it like on my next breeding attempt.
It would be a really great achieve, right? I mean, I don't know how far is for example, the scientific community in this field, but sounds like a great achieve.
Well, scientists have been modifying mammals for decades now, right? So,
but also to cure disease.
Yes. And so that's the issue, right? So like nobody's ever cured a genetic disease in dogs by genetic engineering because there's no motivation, right? So like the people who are motivated to cure these diseases are the dog breeders and the owners. The people who have the tools and technology to actually do it so there's a gap between those people. Like university of wherever may have the tools, but they're not working. They're trying to cure cancer in humans. They're not trying to cure,
that's that's completely right. That's the long tail Francesco was talking about. That's you can have a specific interest that is not covered by some institutions or a pharmaceutical company that has some bigger and more with more money behind problem.
Really and my goal is to get a really simple, cheap technique that's sort of within the wheelhouse of what dog breeders can do, because dog breeders already collect sperm and do artificial insemination. So if I can get it as simple as collect sperm, modify the sperm with a simple procedure, then do artificial insemination, I can teach other dog breeders how to do it. And I can make a piece of DNA that uses something like CRISPR to make a genetic repair or even a genetic enhancement. And I can distribute that amongst the dog breeders. And they can say, okay, well, I'm going to have, so suddenly thousands of Dalmatians or whatever can be born with, like all Dalmatians pretty much have this genetic disease called hyperuricemia. If I can make a fix for it and just show the breeders how to do it, they can all do it at once and fix the whole breed in one go.
Wow.
In one generation.
So you can actually fix like a whole race of dogs in actually one generation of few decades.
Yeah. I mean, you could do it in 3 years.
Wow, this is amazing.
I mean, it's like just long enough for those modified puppies to be born, grow up, and become a new generation of breeders, and it's done.
Yeah, because if you're doing the sperm cell, it's already on heritage, right?
Exactly.
I'm gonna translate it. Vai, Gian.
Praticamente gli stavo chiedendo, dato che prima ci aveva detto che ora quello su cui sta lavorando è curare le malattie dei cani, dato che lui fa l'allevatore, ed è una cosa che comunque le grandi aziende non fanno perché non ci sono grandi interessi economici dietro, perché una volta che l'hai risolto comunque l'hai risolto quel problema lì, oppure le università hanno problemi più grandi come il cancro degli esseri umani a cui pensare, quindi giustamente questa è l'idea del biohacker che può andare a risolvere i propri problemi o dei piccoli problemi della lunga coda, come diceva Fra prima. E gli ho chiesto a che punto era in questa cosa qui. E lui ci ha detto proprio in breve che è riuscito a modificare, quindi a modificare geneticamente le cellule dello sperma dei cani, però non è riuscito a fecondare, quindi ci ha raccontato tecnicamente come stava cercando di risolvere questo problema e in 3 anni si potrebbe risolvere, cioè se uno riuscisse a farlo, diciamo, a risolvere proprio i problemi di tutte le generazioni di cani, cioè una volta che risolvi...
Esatto, e la cosa pazzesca è che fondamentalmente, come in qualsiasi ricerca, la sfida non è solo capire cosa fare giusto, ma soprattutto capire dove stai sbagliando. Quindi adesso ci stava raccontando che con delle nuove idee, con delle nuove suggerimenti che ha ricevuto anche da altri colleghi, ci si sta avvicinando e questo è molto molto interessante perché effettivamente poi ha un effetto, diciamo, palla di neve, perché una volta che viene fatto una volta, questa, diciamo, modifica, una volta che arrivi al successo, lo puoi condividere con tutti gli altri in tempo zero, perché la tecnologia è veramente veramente cheap, non costa tanto. Quindi è solo arrivarci ad averla.
And there's other sort of peripheral impacts to that too, even beyond curing genetic diseases. You could enhance dogs' abilities. Like, so imagine what we could do if we had dogs that could smell coronavirus.
Wow.
You know?
Without being
correct.
affected.
Yeah, without being affected, because dogs are resistant. Now, cats actually can show symptoms.
Ah, ok.
You could have dogs. If you had dogs at every airport that could smell coronavirus, even asymptomatic people who were giving it off would
crazy.
have the smell.
It's crazy.
I mean-
but because it's easier with dogs, what's the point? Apart from the fact that is allowed, that is a good thing because it's not allowed on human, I guess. But it's
Right.
also easier to do it on dogs.
There's actually been more research on modifying humans than there is on dogs. But but most of that's like because we're more focused on human genetic diseases than on dog genetic diseases. But like you could, in theory, have a gene therapy that was like a nasal spray that modified their smell receptors
Wow.
to give them the ability to smell just about anything. So anything that could bind to a smell receptor and be specific could kick off that thing. So you could actually have a dog. You could take all those airport security dogs and give them the ability to smell coronavirus.
Is some of your friends working on that?
No, nobody's working on that.
Okay, just to know.
Yeah,
It
but
would
that's
be
the thing.
great, actually.
Yeah, but like designing a novel olfactory receptor would take a minute. But if you had something like that, like I think that's the only realistic way to do biosecurity because like all the
Biosecurity. I love that. Biosecurity.
Yeah, that's the first time I heard this word. Thank
Yeah.
you for that, David.
Yeah, I went to a whole like biosafety, biosecurity conference not too long ago. But you know, how do you detect an incoming pathogen? You know, I mean, how do you know that it's on an airplane or that it's in a passenger? Because like you can take everybody's temperature, but like with coronavirus, how many people are
That's
asymptomatic?
right.
Yeah, that's completely right.
And then how many people are contagious but asymptomatic, and so you have to shut down the world because you can't just selectively identify people. And the tools that we have to identify people are complex lab tests. So you know,
Yeah.
you get the test, and even if you have them that you can do in a few minutes, you can't take 20-30 minutes with every person trying to
That's
go through
right.
airports.
Yeah, and there is another problem that it doesn't like work every time on the first try. So
Right.
you can just check somebody and say, yeah, you're okay, but instead it was contagious. Ragazzi, ci ha appena raccontato una roba fichissima, cioè fondamentalmente una delle tecnologie con cui si potrebbe arrivare attraverso il biohacking o comunque il gene editing in generale è il fatto che prendiamo per esempio questa situazione qui del coronavirus. Oggi se tu vuoi capire chi è infetto su un aereo, l'unico modo hai prima di tutto sentirgli la temperatura, gli spari la pistoletta e ti dice se ha la febbre o no, però ci sono persone che non hanno i sintomi nonostante siano infette. E quindi come fai? O fai i test a tutti e in più i test non è detto che al primo colpo funzionino, però in realtà tu potresti anche avere uno spray che fa inalare ai cani, che diventino in grado di fiutare, proprio letteralmente fiutare, se qualcuno è infetto oppure no. Quindi biosecurity, sicurezza biologica. So the thing that I'm amazed is actually you can use biology way better than technologies. Like you can actually program biology to achieve stuff that like digital or regular technology can never dream to achieve in that,
Right.
in that quickness, in that time.
Yeah, and that's the interesting thing, because like a smell receptor, binds to a substance, whatever it is, and then just releases. It basically ends up causing a nerve impulse, right? So it's like actually a complex chain of things that happen inside the cell, but it releases a nerve impulse, and then it just goes to the animal's brain, and it goes, "I smell that," instantly.
Yeah, so
And
you just have to allow them to be triggered from that substance.
exactly. And then you just walk up, and then as everybody's going through, the dog's just smelling everybody, like we already do for drugs and explosives and things like that.
That's right.
Wow.
And here in chat, they're interested about the economical world, the business world around biohacking. Is there a market for that? Or another question that I read in the chat is, but if everything is for free, you're doing everything for free, how do you make a living? How do you make money?
So I work in the oil field, so I do this nights and weekends.
Okay.
Yeah. So unfortunately, it's not my full-time sort of thing. So I go to work. I was there this morning, working in the oil field. I took off early today to be here with you guys.
Thank you very much.
Thank you very much, David. We really appreciate it.
No problem. I didn't want to be there anyway. So there's things like that. Most everybody's got a day job. Some people make a little bit of money with their biohacking with teaching, and some people sell supplies and things like that. But there's really not a great model for how to make money at being a biohacker. Like I get paid some from my Patreon, and like I get like $7 a month from YouTube. So technically that's something. So I mean, if you were to so like as far as my project goes, what pays for like how do I buy pipettes and stuff like that? Originally, the dogs paid for it. So like I breed dogs, so I'm using it to help them. They're helping me help them. So some of that was that, and then some of it was just I would just pay for it out of my paycheck, which is why everything was like home built and as cheap as possible. But it's a lot easier now with the Patreon because I'm getting patrons, and so now I can like afford things when I need them. I don't have to save up for 2 months. I can just go get something if it costs $400. So it's starting to grow, and a lot of that since the Netflix documentary came out, a lot of people found out about my work and wanted to help out, and I super appreciate that because it really is enabling to have even just a little bit of regular money dedicated to that thing. And so some of that's there, but as far as like how to make a living being a biohacker, I don't know yet.
You don't know yet. You didn't find out yourself yet.
I mean, I think when you're gonna achieve your goal about cure this disease or enhance dogs, you're gonna have a nice stream of revenue if you put that on the market.
Yeah, and that could be something, because I could also like teach classes, teach other dog breeders how to do genetic modification of dogs. That way, you like have a big seminar or something. You come for a weekend and I show everybody how to do it, kind of thing.
Are you doing
it?
Yeah. Already? Are you doing it already? Are you doing classes? No.
So I actually have taught some classes online for genetic engineering, but it's more like the basic stuff. But as far as like what I would teach dog breeders, no, because I want to make sure that I'm done with the protocol, because once it works, then I'll know what to teach them for sure, right? So because I may chase this method for a while and then decide, I need to make some very fundamental changes, and I don't want to have taught anybody wrong.
Yeah, that's right. Yeah. Another question from the chat was about how long does it take, for example, in your situation, where from the moment you started up with biohacking to the first result, to understand something about it and make some result?
It depends on how big your project is, right? So like from the first time I got the idea, like my first thought was like it was like June 2015. I was like I watched a TED talk and they were talking about CRISPR and genetic modification and de novo synthesis and that sort of stuff. And I was like, I need to try this in dogs. This is the thing we've been looking for. And it probably took me until about 3 or 4 months of just reading stuff. And then like my first modified bacteria was probably December or January following. So a few months before it's like, okay. But I also didn't get like one of the kits. So like if you buy a kit for like how to genetically modify bacteria, yeah, you can do it in like an afternoon, right?
Oh,
but
wow.
Well, like 3 days really. But if you are sort of starting from the bottom and sort of building everything, because that didn't exist, right? So like the biohacking kits and stuff didn't exist when I started. So
in which year did you start?
2015.
Yeah.
It's crazy.
Yeah. It's like mid-year 2015. And so by the time you get like small results, like I have genetically modified bacteria, that's pretty fast. If you're trying to like build it all from scratch, a few months of reading and learning. If you buy a kit, a few days. But you don't necessarily have the understanding. Like the kit's educational in the techniques, but if you build it from the bottom, you get probably a more rounded understanding. But like I actually took a calendar when I first started doing this and worked out a heat cycle that I wanted to try it on the first time, and then built a syllabus for myself backwards up till now to have like dates I needed to learn specific things by. And I think I set that for it was a year basically.
Okay.
Before I tried it the first time, but it didn't succeed, right? So it's been 5 years since.
Fair enough.
Okay.
But like I modified bacteria way before that, so it's like a few months. So it depends on how big your goal is. If your goal is to do something that's never been done, like genetically modified dogs through sperm-mediated gene transfer, you might have to settle. Yeah.
Just a quick translate, then we go to the end because I see we are live from a lot. And ragazzi, praticamente gli abbiamo chiesto, ora mi sono dimenticato pure tutte le domande. La prima era il mondo, quello che avete chiesto voi, cioè quanti soldi girano dietro e come si fa a guadagnare con questo lavoro. Lui ha detto che praticamente lui ha un altro lavoro proprio perché non c'è un modo per guadagnare da questo lavoro, o almeno lui non l'ha trovato. E poi l'altra cosa che gli ho chiesto, dopo mi sono già dimenticato.
Sì, poi quanto tempo ci vuole da quando diciamo vuoi iniziare questo percorso a quando puoi avere i primi risultati. E chiaramente principalmente dipende da qual è il tuo obiettivo, perché per modificare dei batteri, ad esempio averli fosforescenti o che brillano al buio, basta che compri un kit e segui le istruzioni, quindi in un pomeriggio lo puoi fare. Però è chiaro che se hai un obiettivo più ambizioso, più complesso, che magari non è già compreso in un kit che puoi ordinare e applicare, diventa una ricerca, e lui comunque ci sta lavorando ormai da 5 anni.
E lui ci ha messo qualche mese, diciamo, per ottenere i primi risultati, però al tempo non c'erano kit. I have a last question. I don't know, Fry, if you want to ask something else, but it's something we just talk about a bit, but I want to hear from you what you think about it. And it's about the dangers of let everybody deal with something that can biological alter themselves or others.
Yeah, so I think, as far as the dangers go, like there's some things that you have to know. Like obviously you can't just say, oh, I'm just going to inject myself with some bacteria that have DNA and it's going to be a good thing.
Yeah.
You have to know what you're doing. And so that takes time, it's just like learning programming. You might write a program that breaks your computer, right? But most of the time, the program that you're going to write is just going to fail, right? If you don't know what you're doing. Not going to damage your equipment. But if you look at like, for example, the things that are restricted, like I can't go buy tuberculosis bacteria and just grow it up in my lab for me to experiment with. There's restrictions on that sort of stuff. And obviously we don't want people just like growing up tuberculosis in their fridge, or botulinum or something like that. So human pathogens have restrictions on shipping and things, and even like agricultural pathogens like agrobacterium.
But there is a market for that, right? So somebody can buy a pathogen. That's the point.
Yes.
Okay.
Yeah.
Know
so
that.
do it all the time, right? It's like virology labs have to have
everything is on sale in this world.
Oh, you can even get like custom genetically modified mice lines if you want. Like you're studying like some genetic disease, you can order a bunch of mice who've been engineered to have that disease so that you can then experiment on them.
Okay.
Everything's available. But like some things are extremely restricted. Like smallpox is only in a handful of labs in the world because otherwise it's extinct. Where things like, the flu is in many, many labs. HIV is in hundreds of labs all over the world. But we're not as worried about HIV breaking out because it's not as contagious as like smallpox. And it's also, we have effective medication. So if you accidentally expose, like if you're a researcher and you accidentally stick yourself with a needle and now you have HIV, there's medications that'll keep you alive. If you accidentally stab yourself with smallpox, admittedly, we do have a smallpox vaccine, but you may not realize you've contracted it and spread it around town before anything happens. So those sorts of things that are more dangerous are very strictly controlled. And that's reasonable. There's no reason to be crazy. I have no need for Ebola,
Yeah, that's fine.
Nor do I want Ebola,
Okay.
But some people do go overboard with it and they want to restrict anything.
So you don't see the danger so big. It's like, for example, I make a metaphor. It's like everybody can have a knife and you can kill yourself or you can kill others. That's the point, basically.
Yeah, exactly. Okay. And also the things like robotics, I think is the one I use a lot. Like, you could make a killer robot and send him on a rampage, right? But nobody really does that. People don't really want to kill people with killer robots. Most people, like the people making killer robots, are the military, right?
Yeah, exactly.
the big guys.
Yeah, most people who make robots want to just like make a crazy thing that does something silly and make a YouTube video out of it, right?
Okay.
Yeah, probably that's gonna be the first outcome.
Right. I mean, that's what people do with robotics. So they like make two robots that fight each other,
Yeah, that's right. Quick translation, praticamente gli ho chiesto dei rischi di questa cosa qui e cosa ne pensava, e ha detto che tutte le cose più pericolose comunque non sono in commercio per le persone normali, quindi cioè teoricamente ho scoperto che c'è un mercato dove ti puoi comprare le malattie, cioè, tipo certo. L'Ebola o
la smallpox, non mi ricordo come si traduce.
Sì, però diciamo quelli sono restricted solo per gli operatori del settore, giustamente, grazie a Dio, aggiungerei. Per il resto è come dire invece che io ho fatto l'esempio del coltello, che tutti possono comprare il coltello, ci puoi affettare il salame o ci puoi andare a coltellare la gente, e lui ha fatto l'esempio della robotica, che chiunque può progettare un robot che va a uccidere le persone e giustamente Fra diceva che è più facile che questa roba qui la struttura un governo. There is another question from the chat.
The last one.
Chemistry is just way easier to kill people with, like chemistry and physics. Like if you just hate your neighbor and want them to die, it's a lot easier to hit them with a hammer than it is to genetically engineer something to try and kill them. And also it's like, if you just want to hurt large numbers of people, it's a lot easier to do that with like toxic chemicals dumped in the water supply,
right.
Or explosives it's like, look at all the terrorist attacks. It's mostly been explosives, because explosives are a really easy way. Instead of spending years trying to engineer something, you just cook up a bomb, the instructions are on the internet, and boom, you kill a bunch of people.
That's right. Faccio un altro esempio con per esempio gli elementi chimici o gli esplosivi, che giustamente chiunque se li può fare e mandare i pacchi in giro, come abbiamo già visto in passato. There is another question from the chat that is, do you think biohacking can overcome medicine in the future?
I see it differently. I don't think I think they fill slightly different roles, right? So I think a lot of people see it as like an alternate way to do things. I think the rigorous, centralized, big sort of system is useful. You know, it creates good things. It also creates bad things, and it has sluggishness. I think of it like you have this big sort of nucleus. Like, have you ever seen a slime mold?
Yeah,
I don't know if you ever.
the slime.
Yeah, so there's slime molds, and they have like a central nucleus over like a resource-rich area, and then they sort of like reach out into the dark and sort of feel around until they find something else that's good. So that's sort of how I see it.
They're like a monocellular organism, like different units that thinks as one. Correct?
Exactly. So that's what I think. Like you have all the universities and institutions and companies and governments all sort of as this central thing with this big system that creates, you know, cures things and it does things and stuff like that. But there's all this space around them that they don't explore, you know? And so I think it's like the biohacking is sort of the fuzzy fringe that can like, oh, what's over here? Or maybe there's something over there. And most of it will find nothing. But if you find something good over here, then you can be like, hey, look, there's sort of fertile ground over there. And you can incorporate that into the main system. Because it may be something crazy, like, you know, completely ridiculous that nobody would think of. Like, let's put a little grape juice in our you know, DNA transfection material because some crazy guy decided to try that. But it's ups your transfection efficiency 20,000 times. And then, bam, we have breakthroughs in genetic engineering technology and we cure all these diseases because somebody tried something stupid, you know?
Yeah. We talked yesterday with another guest about mistakes and the good outcome of mistakes a lot of times. Or
like antibiotics. Totally, you know, that was just a guy who was being sloppy at the lab.
Yeah, that's right. That's exactly.
Just a sloppy hand.
Yeah. You know, and so I think there's room to explore the edges, and I think that's the role biohackers can fill.
This is beautiful. David, I want to thank you for the time you spent with us and for the precious information and experience you shared with us and with the community. I know it wasn't easy with the double language thing, but you've been great, and we really appreciate that. Thank you very much.
Thank you very much, David, and all the chat. Thank you for your interview, and we hope to help you also in your Patreon with your Patreon, because we can show this video hopefully to a lot of people. Okay. So we will put all your reference on YouTube so they can reach you. And thank you very much again. It was really a pleasure, David.
And thank you to all the guys in the chat too for all the good questions.
Yeah. Okay, guys. So for tonight, it's enough. It's almost 2 hours with David Ishee, our biohacker. And see you tomorrow, 7:30. Yeah. Ciao.
Ciao, ragazzi.
Ciao.